I will begin with a word of prayer. It's time to get started. Ahem. Dear Father, we thank you for this day again. I thank you for this class. Just ask you to guide our steps today. Help us to glorify you what we do and understand a little bit more about energy and how to use it to understand your creation, Lord. In your name I pray, Lord Jesus. Amen. All right, so I hope you guys watched the videos. If you didn't, well, then you should. Now, so I wanted to give another example of how to calculate the potential energy for a given force field. So, example 1. Suppose we're given the force field is, I don't know. Let us say x cosine of x squared minus xy squared, comma, I don't know, e to the y minus x squared y. I think this will do it for us. All right, so I believe this is a conservative force field. So let's try to find the potential energy function for it, all right? So the question is, this is equal to minus the gradient of the potential energy. We want to find U, all right? So if we look at this, we're up against two equations we got to solve here. On the one hand, we need minus partial U, partial x equals to x cosine of x squared minus xy squared. But we also need to solve minus partial u partial y equals to e to the y minus x squared y. All right? So these are the two equations we need to solve. Now, I personally like to put the minus on the other side. So let's just go ahead and do that. I'm going to watch careful here. I'm about to erase this minus here and put it over here, which makes this a plus. I'm going to erase this one. That puts a minus here. It makes this a plus. All right? Okay. So then there are basically two strategies for solving for the potential energy, and I'm going to show you the strategy which is, let's say foolproof, in the sense that if it doesn't work, it means that the potential energy function doesn't exist. All right, so here, I integrate with respect to x holding y fixed. And so what that gives me is u of xy is equal to apparently minus 1/2 sine of x squared, all right, plus 1/2 x squared y squared, plus some constant. Now here I'm integrating with respect to x holding y fixed, so that means that this constant could possibly be a function of y. All right, so let me call this equation right here star, and what we're going to do is we're going to plug star into here, all right? What that gives me is, let's see here, partial y of, minus 1/2 sine of x squared plus 1/2 x squared y squared plus C1 is equal to minus e to the y plus x squared y. All right? All right, so what's the partial derivative of the 1/2 sine of x squared term with respect to y? This what? What happens here? That's 0, right? Because we're just differentiating a function of x with respect to y, so that's 0. And this piece here gives me x squared y, because the 1/2 and the 2, they'd be canceling. And then I get plus dc1 dy. The reason that's a total derivative is because, remember, c1 is just a function of y alone, so that's really just dc1 dy, right? Now that's supposed to be equal to minus e to the y plus x squared y. Good news, this part cancels, right? That part cancels. And as such, we're off to the races here, almost. So now we have to solve dc1 dy equals to e to the y. I think you guys can do that. What's c1 equal to? c1 equals what? Almost, but I've got a minus here, right? So minus e to the y. And in principle, I could have a constant. And I do actually mean an honest to goodness, honest constant here. Not actually a function of y, but a real constant, all right? And so put this all together, what do we have? We have found the potential energy function for this force is minus 1/2 sine of x squared plus 1/2 x squared y squared minus e to the y plus a constant, all right? Now usually what I do, guys, is I don't even bother with that constant. What do I usually do? Usually I just put the constants equal to what? 0. Technically speaking, you can make the constant whatever you want. This is always a freedom we have with potential energy. The absolute value, numerically speaking, of potential energy is not physically meaningful, right? It's always, you choose a reference for where potential energy is 0. So we do have freedom in what we choose that constant to be. You could make it 0 if you wanted. So any questions here before I go on? Like, now that we have this, we could calculate the work done by this force, right? Like if I was to say, you got a path that goes, say, from 1, 1 over here to, I don't know, 8 minus 2 or something, right? And you wanted to find the work done, calculate work done by F along C. How would we do it? We would calculate the integral of F dot dr along C. That's minus the change in the potential energy, right? But since we know the potential energy function, this would be like u of 1, 1 minus u of 8 minus 2. So we could calculate the work done simply using the formula we have right there. We just plug the points in and take the difference, right? So I guess I can work it out. Minus 1/2 sine of 1 plus 1/2 minus e to the 1 plus the constant, right? Minus 1/2 sine of 64 plus 1/2 of 64 times 4 minus e to the minus 2 plus the constant. You see that physically speaking, it doesn't matter what that constant is. When you actually go to calculate something that's directly physical like work, right, the constant cancels out. See, the choice of C naught is immaterial to like motion and such. See that? So whatever this value is, that's the work that's done by this force field, the given force field along that curve. Now, which curve, by the way? Which curve is it from that point to that point? Did I tell you the nature of the curve? I didn't, right? I didn't tell you if it's a line segment or, you know, what I've pictured, right? For all I know, it could be this, right? It doesn't really matter because this force is path independent. It only depends actually on the initial and starting point, because we can calculate the work done simply by taking minus the change in the potential energy function. All right? Any questions? Okay. Another thing So I mean, maybe it's instructive to do one more example of this nature just to see how it doesn't work. So like, let's take a force field which is actually not conservative. So if I do like x, comma, 1, I don't think this is, well, that might be conservative. I think if I do like x, comma, x, this is actually not conservative. Yeah, I don't think this one's conservative. Let's try. Let me make this a little bit more exciting, x squared. Let me make this an x squared and an x, that was supposed to be a squared, and an x cubed. There, that's a little bit more exciting. And let's try to find a potential energy function. Like, is it possible? We're going to find out, no. It's not, oh, did you move the camera? Thank you. So let's work it out. Let's try anyway. So we'd want to try to solve partial u partial x equals to minus x squared, and partial u partial y is equal to minus x cubed. I just went ahead and moved the minus to the other side, right? So we integrate the first equation with respect to x. What do we get? This tells me u of x comma y is apparently minus 1/3 x cubed plus some constant function in y. All right? By the way, I'm doing this for two-dimensional forces, but the same arguments hold for like three-dimensional forces. We do live in 3 dimensions, so I do ask those questions too. So then what? So this is my first, you know, this I've taken care of the component 1 for this equation, but how about component 2? Plug star into here, what happens? We get, what's partial u partial y is equal to what here? It's just dc1 dy, right? And that's supposed to be equal to what? That has to somehow equal what? Minus this minus x cubed, right? So this is just function of y, and over here, oops, right? This is absurd. You can't have this. How do you, I say something's just a function of y. What does that mean in terms of calculus, by the way? Here's what it means in terms of calculus. The x derivative of c1 has to be 0. That's what we mean when we say c1 is just a function of y. It means that the x derivative of it's 0. So of course the x derivative of dc1 dy is also 0. Right? But if you differentiate this equation here with respect to x, you get 0 on the left-hand side, and you get minus 3x squared on the right-hand side. So we get 0 is equal to minus 3x squared. You can't have that, right? So what does this all mean? It's not conservative. So we find, so this is impossible. And so that tells me that no potential energy function U such that the force is equal to minus the gradient of the potential energy exists. This force field is not conservative.
How did we get negative x cubed in the first place?
Oh, I'm plugging star, that into here. So that is just literally the plugging in. It's this is going there. And this is going there. Yeah. Exactly. So this is one way you can learn something's not conservative, like this, all right? I will tell you guys another helpful theorem to know about, and I'll just tell you. If your vector field is like p comma q, all right? Then you need that partial q partial x has to be equal to partial p partial y in order for f to be equal to minus the gradient of the potential energy. So that's a helpful little theorem to know about. That gives you a quick way to check without, I mean, of course you could always go through this derivation like I just did and and just find out, oh, well, I can't actually calculate the potential energy, right? You can do that, right? Or you can make this quick, simple little check at the start of the problem. Like this one, my P is what? So here we have P equals to x squared, and my Q is x cubed, right? So partial P, partial Y is what? 0. Partial Q, partial X is 3x squared. As you can see, these are not equal, which tells me that this is not a conservative vector field. I can, yeah?
So the theorem,
Yeah.
lets you know whether or not it's conservative.
Yeah, yeah. And the theorem, if you want to know where the theorem comes from, it's not particularly deep. Pretty much, if you have this, right? Because the second partial derivatives commute, like it doesn't matter which order you do them in. That means that if the x component is the x derivative and the y component is the y derivative of the potential energy, it should be the case that the y derivative of the x component is equal to the x derivative of the y component, because the partial derivatives commute, which means that these two components have to be interrelated in that way. It's because of this rule of calculus. That's why we get this theorem. Now, again, so it just gives you a simple criteria to check on whether or not this is going to happen to you when you try to find the potential energy. Yeah.
And just clarifying, the reason this is possible is because the function of y can't be equal to just x. It needs to be like the derivative of y to y something.
Possibly.
For example, it was
Yeah. Well, I hesitate to describe it at that kind of level of description because there's like so many possibilities. Like a constant vector field's conservative. Would that satisfy the criteria what you're just saying? Like there's no y dependence. If I have vector field F equals to 3, 4, there's no y dependence here, and yet it's conservative. The potential energy for that is minus 3x minus 4y. Yeah.
What if it was like y squared x squared, or y squared x?
Now we're in the lightning round here. G equals to what?
Y squared.
Uh-huh.
X to the third.
This? Or is it both
No,
in
like the y component is x to the third.
this?
Yeah.
Let's see here. So the x, partial x.
They're both 0.
But maybe if we... But isn't... so this is my P, and this is Q. But partial P partial Y would be 2Y.
Oh,
You got the right idea, but we need to flip the script. Like if I just put my x cubed over here and my y squared over here, then sure, then you have the y derivative of the x is 0 and the x derivative of the y component is 0. And the potential energy is what? I can write it down, minus 1/4 x to the 4th minus 1/3 y cubed. There you go. Like, we don't have to do this multi-step integrate substitute process. We can just guess the potential energy also. Do you guys agree? If you take the gradient of this, the x part gives you x cubed. The y derivative gives me y squared, because the 3 and the third and the 4 and the 4th from the power rules cancel, and the minus goes away because I put it in there. Now, you might not see that yet, but my point is once you've done enough of these problems, you can just write down the potential energy. Like, we don't have to go through all of this if it's simple enough. The nice thing about this way of doing it is you don't accidentally, like sometimes a typical error is you guys will give me like double this piece as opposed to just needing one of these. A lot of times I see students give me 2 of those or something. But anyway, again, if you haven't watched the videos yet, please do. I do talk more about these sorts of things in there. So enough about this part of it. Let's get on to some examples, yeah? So if I can find my juice. Did I answer your question? I don't know.
Yeah.
Okay. So I have a couple different goals for you guys in here. One is to understand what is a conservative vector field. How do we understand its structure? There are, three major ways, I suppose, to look at it. We can look at it in terms of path independence. We can look at it in terms of, is the integral around a loop 0? And then, of course, the part that's perhaps more physically interesting is the force actually minus the gradient of a potential energy function. That's interesting because if it's the net force, then we have energy conservation. All right? But we want to understand as best as we can the interrelation of these ideas. And so that's part of your homework. The goal of the homework is to try to get you to see these things, all right? So example 3. So let's talk about gravity, actually. So if this is y and this is x, right? And the force of gravity is like 0 minus mg. Well, it should be relatively clear that that's minus the gradient of mgy. See, because in 2 dimensions, if I take the gradient of this and mg is a constant, I get that. Basically, the point is that the gradient of the y function is simply partial y, partial 0, partial x, partial y, also known as 0, 1. So because of that, this is true. What this all means is that in this context, the potential energy due to gravity is just minus mgy. Actually, that's not quite right. What is it? Is it minus mgy? This is supposed to be what? Minus so the minus is needed because that's how we connect the force to the potential energy, right? So in fact, potential energy is just what? It's just mgy here. Now if I write mgy, I'm making the potential energy 0 where? At the ground, wherever y equal to 0 is, right? Assuming y equal to 0 is the ground, there you have it. There, of course, is another scheme, which is that we're talking about 3 dimensions, right? We can talk about 3 dimensions as well. If my force is 0, 0 minus mg, right, then I would want this is equal to minus the gradient of what? Mg what? Z, right? So in 3 dimensions, we could write the potential energy for gravity is just mgz. More generically speaking, sometimes if I don't want to label x and y and z and stuff, I just use h for height, right? So like, if you just want to think about h being the altitude, you can do that. So potential energy due to gravity is just mgh. So let's look at an example here. So if I have a building and I shoot a cannonball here with mass m at speed v naught at angle theta, right? Then we go on some kind of trajectory over here, and then bammo, it hits the ground, right? And let's suppose that the height of this building is h. So my question is this, what do you guys think? Is the speed at which the projectile hits the ground, is it going to be larger for like theta equal to 45 degrees, for theta equal to 90 degrees, for theta equal to 0 degrees? Like, what angle maximizes the speed at which the projectile hits the ground? What do you think?
Straight up.
Straight up, straight down? Yeah, let's find out. So here we go. Energy. So first of all, we're neglecting air friction, all right? To be clear, we don't know how to do that mathematically. If you want to talk about air friction, you need to take the other section of physics. I'm sure there's like a week that Dr. Bodares spends solving one problem with numerical methods in great detail or something. I've heard, which is awesome. But that's not my course. So anyway, so here we can conserve energy because the only force that's in play is gravity. We're neglecting friction, right? So the net force is gravity, and gravity is a conservative force. I just wrote the potential energy functions for it over here. So what that means then is energy is conserved. So we can say that the energy at the beginning is equal to the energy at the end. What's the energy at the beginning? Well, the energy at the beginning is mgh, that's my potential energy, plus 1/2 mv0 squared. So that's my initial energy at the moment we fire the cannon or launch the water balloon. No, it's a cat. We kicked a cat at angle theta with speed v0.
He was an evil.
He was an evil cat. That is redundant. So I appreciate that.
Did Batman kick the cat?
Did Batman kick the cat? Well, it could have been. It might have been Ron Swanson.
Robert Downey
Shot the
Jr.
cat out.
I'm open to it being Ron Swanson or Batman. Maybe there's a fictional universe where those are the same person. Let's see here. So there's the final velocity. So the final kinetic energy is 1/2 mvf squared. And what about the potential energy? It's 0. All right, so let's solve for VF. VF is equal to apparently the square root of 2gh plus v0 squared. So the good news is that you are all correct. Every angle maximizes, every angle minimizes. It doesn't matter what angle you pick, it's the same speed. Because the speed is independent of the angle. It's just dependent on the height and the initial speed. So I derived this earlier in the notes using kinematic equations. It takes me about a page. I hope you appreciate it took us like 5 minutes now. Energy methods are stupidly simplifying for kinematics problems. Now, are those trajectories all the same? Absolutely not, right? Like, if I choose a high angle, it's in the air much longer, right? If I was able to achieve minus 89 degrees, obviously it gets to the ground much faster, right? But in all these different scenarios, it hits the ground with the same speed, assuming there's no air friction, right? So, I mean, if there actually was air friction, I mean, there is, of course. If we could actually account for that, then that would be a very much path-dependent phenomena, like we saw with the work integral, right? The work done by friction is far from path independent. In fact, it depends on the path quite a lot. So here's a pro tip for you. If I, on the next test, ask you to calculate the work done by a force, right? And I don't tell you the details of the path, if I just tell you the endpoints, the only way that problem makes sense is if the force is conservative. Think about it, right? I can only ask you to calculate work done between endpoint and starting point if it doesn't matter which path you chose between those points. And that is only going to be the case if we have a conservative vector field. All right, here's another one. Example 4. Let's see here. Oh, thank you. I know I top hat it already, but I try to hand this thing around sometimes, so there we go. So here's another sort of standard example. Suppose you have a box, all right? And it starts up here, all right? So the center mass of the box is basically here. So it's at height h above the ground, all right? And this is angle. This angle's actually let's not make this h. Let's make this. We don't know what this is. Let's say that this length here is L, all right? And then it comes down here, and there is a spring with spring constant K, all right? And it starts with the initial velocity being 0, all right? It slides down the inclined plane, right? Goes over there to the spring, and then it compresses the spring. The question is, how far is the spring compressed? All right? Do we understand the question? All right, so I'll draw sort of, here's the end. So this is the start. The end, it's, you know, I'll draw the picture. So maybe this is the equilibrium. So like how far did it compress the spring? All right. How far is the spring compressed in this situation? And we'll let the angle be given to be theta here. All right. So given M starts from rest and slides without friction, how far does spring compress? And we're going to let the spring have spring constant K. So we can use energy conservation here again to solve this problem because there are no non-conservative forces, right? Like if we think about this as a system, there's gravity, right? And there's the spring force. Both of these are conservative forces. So like the energy that it takes to compress a spring is stored in the spring in the form of potential energy of a spring. So all right, here we go. So the energy at the start is equal to the energy at the end because everything in play here is conservative. Now if I put friction, if I said this is a plane with friction, well then we'd have to think more, right? We'll do that. But first let's, no friction. So, all right, so we have M, what's the height though? So as you can see, we now have to figure out what's H in terms of L. L is given. So we've got mgh is my initial energy, right? But what is H? Can you guys tell me? 7.2. There are no numbers in this lecture. How dare you? Only letters. Only letters. What's that? L sine theta? I think we can allow that. H is equal to L sine theta. Trigonometry for the win. Yes, I think so. The hypotenuse is this, so the opposite side is hypotenuse times sine. Yep. So what we have then is mg sine theta is equal to 1/2. How do I know that the potential energy due to a spring stored in the spring is 1/2 kx squared? Remember, we worked this out the other day. We integrated the spring force. We got 1/2 kx squared. Yep.
Wouldn't we also need the distance from the end of the triangle to where it's spring?
We would if there was friction. We'll do that next. Well, at the maximum, when the spring has, so the question is, how far is the spring compressed, right? So what happens physically? Is it compresses, right? And then when it gets to the maximum, what happens after that? It doesn't just stop, it springs back. And in this scenario, it actually goes right back up to where it started, and then it comes back down again because there's no friction. It would just go back and forth like that forever. Now, if we added the friction to the part like you wanted, it would compress, it would go back, and maybe if it gets past the friction part, it would go up the plane a little bit less, then it would come back down. If it had enough energy, it would get past the friction part and compress the spring again. At some point in here, it runs out of energy and stops. If there's a friction part to take the energy away. So if we made this part rough, then this would be a different story. Yeah. Oh, good question. I think it was here. Sorry. I blame you guys. You distracted me. Okay, it's my fault. But you notice here that x is equal to what? X is equal to, as it turns out, 2 mgl sine theta divided by k, right? Square root of that. That would be how far the spring was compressed in this situation. Let me take you guys up on your suggestion of making. Let's give it a little rough spot, right? And let's make this spot right here have distance, let's say d, and the spring, the mu sub k, the coefficient of friction there, right? Then how does this work? I'm saying we have the same, basically the same situation here. We've got, some, let's just say initial height h, and up here we've got our mass m. Then down here we've got this part with friction, a distance d there with coefficient of friction mu k. Everywhere else no friction, just for the sake of making the problem not too horrible. We'll just make the friction part just here. And then it comes over and it compresses the spring a certain maximum amount, let's say. Right. Now, first of all, it's not at all clear, unless I put numbers in, that it even makes it to the spring. Right? What is the work done by friction? What's the work done by friction as the box travels over this part right here? What's the work done by friction? So yeah, what's the force? So minus what? Minus mu k mg, right? That's the normal force here, because there's nothing else. So the normal force is the weight. So the weight times the coefficient of friction, that gives me the friction force. Remember, friction does negative work. We worked that out, right? Negative work. So it would be this times d. This is the work done by friction. This is the, this is the total work. Done over the rough patch, all right? Let's put some numbers in so we can make this more interesting. So let's let h be, I don't know. Let's let h be like, say, 10 meters. And we'll let d be like, say, 2 meters. And the coefficient of friction, let's let it be 0.5. All right? And I guess you guys want me to give you a mass. So let's suppose that mg is equal to 100 newtons, just to make things easy on us. All right? If that's the case, what's the initial energy of the system? We do what? We do mgh, right? Which is what, 100 newtons times h, which I said was 10 meters. So what'd you tell me? 1,000? 1,000 joules, or if you like, 1 kilojoule. There we go. It just sounds more cool to say kilojoule, but I'm easily impressed. So, so then what?
Would we have to break it up into two separate, like break the situation into two separate, so we find what the final velocity is just before it goes over?
Yeah, well, right. Yeah, we need to, let's give it a name. Like, we want to find what the total energy is, like right here, right? Let's call that E1. What is the energy at step 1 right there? The first time it just passes the patch, assuming it does. E1 would be what? Would be E naught, right? Minus mu k mgd. Because what happens is we have the initial energy, we lose energy to friction, right? So we should have less energy after we go over that rough spot. How much less energy? I don't know. Let's find out. 1,000 joules minus 0.5 times what my mg was 100, right? And what was the d? 2 meters. So how much do we got? We got 0.5 times 2, natural enemies, gives you 1. So I think we got 900 joules, right? So it's still booking it, still moving, right? Think about this. How much energy does it cost to cross the rough spot in this problem? 100 joules. Does that ever change? It doesn't, right? Because the friction force is independent of velocity here. This is just plain, boring, naive kinetic friction, which doesn't depend on velocity. It just depends on normal force times friction. So what's going to happen is it's going to go past here, right? It's going to compress the spring. It's going to come back. And as it goes back across D, what happens? Loses another 100, right? And it goes back up. It doesn't get as high as it did the first time, right? It gets to a slightly lower height. And then slides back down, loses another 100 joules. It compresses the spring, not quite as much. Bounces back, loses another 100 joules, and this continues, right? Where does the box end up? What's that?
It's on the plane right next to the friction.
Does it? Yeah, I'm really asking. There's really two. I think it's either ending here. It's either ending where I have the red dotted line or here. I'm not sure. You said it's this one? Yeah, I don't know. I have to work it out step by step, right? So, okay. So if that's got 900 joules, then how far does the spring compress the second, the first time? How far does the spring compress? Well, first compression, E2, 1/2 K. Let's call it x1 squared. That's 900 joules. I guess I need to make up a spring constant to figure this out. So we have what? This tells us that x1 squared is equal to, goodness gracious, 1800 joules divided by K. I feel like if you really look at the spring here and you tilt your head and squint, you can see that clearly this spring constant was 180 newtons per meter. I agree. I mean, it's fine. My phone is going to ring here at some point. I can't complain. Okay, so this is 10, right? So apparently x1 is, did I say 180? I really want 18 newtons per meter. So then this is 100, and x1 is 10 meters. Oh, that's a kind of big spring, but I'm going to allow it for the sake of not getting into decimals at the moment. But typically springs involve centimeters and stuff. It's annoying. So what happens then is we compress the spring 10 meters, which is of course ridiculous, and then it comes back. It loses 100 joules. It goes up how high? How high does, how high is the second height? MGH, E2, my bad, MGH, the second height it goes to is equal to what? You told me. I'm sorry, let's try it. 1,000 newtons, 1,000 to 900, comes back to 800. This is 800 newton, 800 joules worth of height.
Wouldn't that just be 8 times 10 hours?
Yeah, I guess, did I ever say, well, H is, so I think it's, H2 is, I think you're right, is 80% of what we started with. I think you're exactly right. And here's why. That's 8 meters, right? So it's going to go to 8 meters after on the first backtrack. It goes to 8 meters, goes back down, loses another 100 joules, compresses the spring to some compression distance. I don't care. Uncompresses, comes back up, loses another 100 joules. Where does it go to next time? Not 8 meters anymore, but now 6 meters, right? So like that H3 is 6 meters. And then we get H2 is 4 meters, right? And then on the third track back, or I've lost count, but the next time it gets to 2 meters, right? It gets to 2 meters. and then it slides back down, loses 100 joules, is going across the rough spot, compresses the spring 100 joules worth of energy worth, comes back and loses 100 joules, and it stops right there. So if I want to punish myself, I ask a question like this on the test. Where does the box stop, right? But I don't think I've ever asked this question. This is like more complicated than what I usually ask. But hey, you started it. Somebody asked about friction. It's all your fault. But all right. Let me. Any questions before I go on here? Where did the what? 800 joules. The logic there was we started with 1,000 of potential energy. Then we lose 100 of it every time we go across the rough spot. So I start at 1,000, down to 900 joules total energy, compress the spring, keep the 900 because spring's conservative, come back here, still 900 joules energy, cost me 100 joules to get back to the other side, 800 joules. I keep the 800 joules. It's initially totally kinetic energy here. As you go up the thing, it gets converted into potential energy. At the height of the swing back, we're at 8 meters, where we've got 800 joules of potential energy and 0 joules of kinetic energy. So, yeah. Another example. What if we have just a plane, angle theta, we have a box, we give it a shove at velocity v naught, and we've got, mu k, coefficient of friction. The question is simply, how high does it go before it stops? Right, what's this distance along the plane? How far does it go up the plane? So what we would do here is we go, okay, so I've got m, 1/2 m v naught squared. That's my initial energy, right? That has to be equal to what?
Zero.
Not 0. I mean, we do give it some push at the start. It's got energy. Yeah, I guess I could say this. This minus the work done by friction, right, has to be equal to 1/2 mvf squared plus what? mgh. Of course, the h here we know is what, L sine theta, right? Of course, as you told me, the highest it gets, right, the vf is 0. What's the work done by friction? Mu k, yeah. Mg, I heard an mg sine theta. Do we believe that? I believe that, yes. I think that's, well, hold on a second. Well, let's think about that, right? So this is the normal force, and this is mg cosine theta, actually, right? So mg cosine theta gives me the normal force, actually, and that's the one that figures into the magnitude of the friction force, and hence the work done by friction. And of course, this is just the magnitude. I have to multiply by the distance, which is, we're calling it L, right? And that's going to be equal to mg L sine theta. Oh, yeah. So sorry, guys.
Didn't even notice.
I know. I didn't either. That's the problem. Hey, look. Apparently, it doesn't matter what the mass is. The answer is the same. Right? I don't have to tell you the mass to solve this problem. It cancels. Now we could solve for L. Right? One equation. If we know the coefficient of friction and we know the initial speed, we can solve this for L, and that's the answer. How would you have solved this problem before? We do what? We just do kinematics, right? We figure out the acceleration, parallel to the plane, and we just figure out where the parallel velocity is 0 and solve for that time and work it out, you know? But this is actually easier than that, isn't it? So, do you guys understand what I'm saying here? And this is a non-conservative process. So like the final energy is equal to the initial energy less whatever we're losing due to friction. That's all that's going on here. I hope that makes sense. Anyway, have a good weekend, you guys. Let me turn off this thing.